All right. How long will be the session? I hope it will be around 1 hour. I'm not exactly sure. So I am sharing the PowerPoint presentation. Please confirm that everybody can see the presentation. And if I'm audible enough, then we can start. All right. All right. So I'll start with the basics of research. We already talked about a lot of things in the previous lecture, but this is to start with the basic biostatistics and things that are very important in order for us to be able to conduct research studies. So these are the things which are important to learn before you're able to understand how to really conduct a research and what kind of study you can do. And because for everything it's very important to know the foundations of it. Once you know the foundations, it's very easy to take it from there. So that's why we decided to first conduct a few sessions on the basics, the biostatistics, the variables, the types of statistics, the concepts of significance, clinical significance, statistical significance, p-value, alpha, beta, and all these things, hypothesis testing, and the measures of central tendency, mean, median, mode, and everything. So if you don't understand anything, put it in the chat box. I'll try to keep a track of that. Apart from that, if I have anything to share, I'll if I have to write something, I might open a whiteboard for that. So starting from the basics, the first thing I would like to talk about is this: statistics. And what's that? So statistics is basically the process of, when we conduct a research, when we do a study, what we do is we organize and we collect data and we analyze it after that, right? Like, for example, I want to conduct a study on the prevalence of something or the effect of a specific drug on something. Or let's say if I'm using research fourth year, whether it's important for second year or not. Yes, it's of course is important. That's why we are talking about it over here. So statistics is when you collect data, either from maybe from the population, or you're collecting data from the already published literature, and then you analyze it, you write about it, and then you play around with it. You look at the prevalence of something, you look at associations between stuff, and you use certain measures, and measures of central tendency. You look at the population, you compare your sample population to the overall population. That's basically statistics. When you are collecting the data, when you're analyzing it, when you're organizing it, when you're writing about it, that's statistics. And for us as math students, since we mostly deal with humans and living organisms, that brings the word bio into it, and that's why we call it biostatistics, right? So I hope that's clear to you. Why is it important to learn the basics of statistics? Because that's exactly what we are doing when we are conducting a study, when we are doing research. That's exactly what we are dealing with. That's what we are actually doing, is dealing with statistics, collecting data, we are organizing it, and we're this is our foundation for a research study. And almost every study has some variables that we deal with. Like, for example, I'm looking at smoking. Like, for example, my variable is exam scores. Like, for example, my variable is age or height, or my variable is hypertension or anything like that. So that's basically the variables, like whatever I'm putting into my data set, The data set is, the variables are the building blocks for the data set. So whatever data I have, it's all made up of variables. And as you know, that variables can be of two types, which either it could be dependent or it could be independent. Dependent variable is, it's dependent, as the name suggests, it's dependent on the independent variable. For example, in the last session we talked about lung cancer and smoking. For that, lung cancer is something which is dependent on smoking. So smoking is the independent variable, and if we smoke we get lung cancer. So that's the concept of and data set. So all the things we include in our study, they are the variables, and they can be of two types, either dependent variables or independent variables. Please keep giving your feedback in the chat box, right? So dependent variables are dependent on the independent variables. For example, if we are getting older, we are getting problems, diseases like cardiac problems, like hypertension, and that's dependent on the age, or let's say consider weight causing some problems. That would be, the weight would be independent, and the problem that is occurring because of it would be, the hypertension, for example, that would be dependent on that, right? So for example, smoking would be independent, and the lung cancer that we are getting would be the dependent variable. Let me share the presentation. All right. To be honest, there isn't a lot in the presentation, and I always like to just you know explain, because presentation just takes the whole idea of understanding. So I would want you to concentrate on what I'm saying rather than what's written, because there isn't anything written. But yep, just for the sake of what I'm talking about, I'll keep the slides. So I hope that's clear up till now. The important next what we'll talk about is what are the types of statistics. So when we're dealing with statistics, there are two basic important types of statistics that we're dealing with. Number one is the descriptive statistics, and number two are the inferential, where we make inferences, right? And descriptive are, which, like the name suggests, descriptive statistics basically describes characteristics of the variables that we are talking about, right? So for example, let's say I'm talking about age, or about hypertension, or about lung cancer, or about smoking. All of these, they're the variables that I'm dealing with. And if I'm describing them, like if I'm describing an individual variable in the data set that I have. Data set, as I said, data set is made up of variables, and out of those variables, if I'm describing one specific variable in my whole data set, that becomes descriptive statistic. For example, if I'm looking at the mean age, if I'm looking at the median age, if I'm looking at the mode of the age for the whole population, these are the descriptive statistics that I'm talking about. The range, the variance, the standard deviation, these are all what we do is we make a graph, or a graph for it, through which we explain it. For example, if you have seen the let me share the whiteboard. So when we're talking about mean, median, mode, range, variance, standard deviation, things like that, I'll explain each and every one of them. What mean is, what a median is, what a mode is, what range, variance, and standard deviations are. Just for the sake of explanation, generally descriptive statistics are when we take a single variable and we describe its role in the data set. Like we are talking about the mean age, the median of it, the mode of it, that's descriptive. Inferential is when we're discussing the relationship between different variables now, right? For example, we talked about in the last session that lung cancer is caused by, let's say I do a study which is smoking and lung cancer. I'll put this example everywhere, so that it's easy for you to understand. Then you can use it for other, in your other studies, and just just for the sake of interpretation. So let's say I say that smoking increases the odds of lung cancer. The odds of lung cancer, smoking with lung cancer, this is I'm making some conclusions, some inferences, right? This is inferential variable now, and inferential variables are the odds ratio, the risk ratio, the attributable risk, the hazard ratio, and everything like that. So if I'm talking about two variables and I'm making some connection between them, showing some association between them. Abdullah, do you have some point? You can put it in the chat box. So when I'm making some association, this is what I'm doing it is, and I'm dealing with inferential variable. But when I'm talking about one single variable, that is basically my descriptive variable, right? It's all right. Even if you can't access the whiteboard, that's fine. I'll just keep explaining. So what the clinical significance of this is, when I'm doing a research study and I'm looking at, let's suppose I'm taking I want to do a study where I want to look at the association between smoking and lung cancer. I took 50 people who are smoking, I took 50 people who are not smoking. What I want to do is, I'm dealing with descriptive statistics, as in what is the age of everyone, what is the gender of everyone, what is the height, what is the how much of smoking are they doing. These are the descriptive statistics that I'm dealing with in my study, right? How many of them are from Peshawar, how many of them are from another locality, how many of them are from Punjab and from KPK, and this is what the descriptive statistics are. Inferential statistics would be something that deals with my conclusion, my inferences, right? So then when I actually follow these patients, and when actually I look at the um, can't you hear? I suppose it's audible to everyone. You can tell me if I'm not. So when I'm dealing with the results, then that's basically the inferential statistics. Now I would like to put 2 points here which are very important. I'm going to the next slide, which is the concept of internal and external validity. Right? When I'm doing my study, and let's say I'm talking about, if whenever we do a research, let's say I want to see if smoking has some association with lung cancer. My actual intention is to put some guidelines to the main population, to the overall population, not just myself, not just my community, not just my institution, not just my city, but the whole population out there, maybe the whole world, maybe the whole country, or whatever. So I'm dealing with what's important to understand is, you cannot take the whole population as your sample, right? You cannot go and get everyone into the study. What we do is, we take our sample size, we take our sample population, and then we compare it to the external population, which is the general population, right? So internal validity is, when I'm talking about internal validity, it's that, for example, uh, how are my groups, my two samples, that let's say 50 people in one and 50 people in group B, group A and group B, how similar are they to each other? And even people in group A and people in group B, how similar are the people in group A to each other, and how similar are people in group B to each other? That tells me about the internal validity. That tells me about the internal validity, because I'm dealing with my population, my sample size internally, right? And how would I tell how similar are they? By looking at their age, by looking at their gender, by looking at where I took these patients from, these people from, by looking at their height, their weight, and all the variables. How much smoking are they doing? Because I can't just take a sample where 20 people are smoking just one cigarette a day, and the rest of the third people are smoking 100 cigarettes a day. Because my internal validity, that's exactly what I want to say. Descriptive statistics are related to your internal validity of the study, right? And the lower, if the group you are taking, for example, their ages are not same, you're taking children with adults, you're taking people from Pakistan and people from America, you're taking people who are smokers, who just smoke one cigarette, and then the other people are smoking 100 cigarettes. That's where your internal validity decreases. That's where your internal validity decreases, because your group, the group you're taking, the variables you're considering, which actually will yield the results, the variables, they're not their description, their descriptive statistics, the mean. Let's say mean age, for example, mean is basically the average. For example, one guy is 2, the other one is 2, the other one is 4, the other one is 4. 2 plus 2 is 4, plus 4 8, plus 4 12. 12 divided by how many of them? 4. So 12 by 4 is 12 by 4 is 4. The mean is 4. Now let's say I took two patients who have age 2 and 2, and the other two have age 100 and 100. What I'm doing it is 2 plus 2 is 4, plus 100 and 100, it's 204, and my mean becomes 102. Or 204 divided by 4 would be something around 50.5, right? So what happens is, when there is a lot of difference between the age, between the gender, between, like, let's say a gender would be, I'm taking 10 males and 90 females, right? My internal validity is decreasing now, because the description that I'm giving to my the variables, let's say the age, the gender, the smoking, the every single variable that can impact my result. Let's say some of them are drinking, some of them are not drinking, some of them are from Pakistan, and in Pakistan, for example, the pollution, the air pollution is contributing to the lung cancer, right? So if there are variables that are not very similar in my group, that will decrease my internal validity, that will decrease the internal validity of my study. Please tell me in the chat box if everybody understood what I explained about internal validity. Someone said, will you explain again how internal validity? Yeah, internal validity decreases when the group you are taking, it does not have, it has a lot of differences in between them. Someone raised their hand. I'll open the setting. You can open your mic if you want to talk. So, or you can put the question in chat. If someone has a question, please put it here. Yeah, the whiteboard, I think we should skip it, because not a lot of people would be able to join it. So let's go without that. How's that? So if someone has a question, just tell me in the chat if everybody understood what internal validity is, and how descriptive statistics are related to internal validity or validity of the study. This is very important to understand, right? So basically when if the internal validity is low, for example, a group has different people and they are not well randomized. We'll talk about that as well, how to increase the internal validity and everything, and even the external validity. Then the results I'm getting, for example, the result I got was that smoking increases the odds of lung cancer. The problem would be that they might be due to other factors, the differences in the group. So what I want to do whenever I'm doing a study, I want to keep my internal validity as high as possible. And this is a point. How do you use it in research now? If in future you're conducting a study, do consider the population you're taking. Don't just go into the population and take anybody into the study. You should have a well-defined inclusion and exclusion criteria of whom you're allowing it to into your study and whom you're not. There should be some well-defined criteria on the basis of which you're conducting the research, right? And it should be written in the paper that you're writing. So this is important. How external validity is how generalizable your results are to the general population. I said earlier, whenever we are doing a study, we cannot take everyone, the whole population, we cannot take them. What we do is we take a small chunk of the population, we conduct a study, and then we give the results. And what we want is we want our results to be applicable to the general population. In other words, I want my results to be generalizable to the external population, and that's the external validity of the study, right? Someone says, is there any relationship between sample size and internal validity? We'll talk about that as well. What sample size does is it impacts the power of your study and some other statistics, but we'll talk about that. That's a very good question, by the way. So it shows that you're understanding. So external validity is like it applies to the population, and it is given to us by the inferential statistics, right? What? The odds ratio, the risk ratio, the hazard ratio, the attributable risk, the relative risk reduction, the attributable risk reduction, and everything. We'll talk about that in a future sessions. But these are the inferential statistics, and what inferential statistics do is they tell us about the external validity of the study, right? And it tells us whether or not the sample that I've taken, does it even describe the general population, or is it like is it a representation of the general population, or is it very different, right? So internal validity is how my groups inside the groups, their variables, their descriptive statistics, how similar are they to each other. The more similar they are, the higher the internal validity, the better the study. External validity is how generalizable my results are to the general population. It is given by the inferential statistics, the odds ratio, risk ratio, relative risk, the hazard ratio and attributable risk and everything. And that's how your results are applicable to the external population. If someone has a question, you can ask. So I'll move to the next part, which is clinical significance versus statistical significance. If you don't understand anything, please do put it in the chat. That will help, because everything that comes ahead depends upon what you're learning right now. So the inferences we make, I'll talk about one other thing as well. We make two hypotheses, right? We make two hypotheses, and one is null hypothesis, the other one is alternative hypothesis, right? Null hypothesis says, for example, if it's smoking and lung cancer, my null hypothesis would be there is no difference in odds of lung cancer for smoking, for smokers compared to non-smokers, right? That's my null hypothesis. Or in other words, there is no association or there is no relationship between smoking and lung cancer, right? And what we do is there is a specific p-value for it on the basis of which we evaluate our hypothesis, right? We'll talk about that as well, what p-value is and what alpha is and how we compare it to that, and how it impacts the results. So when I'm doing a study on my sample population, what I want to do is I want to estimate the parameters of the population, right? If I'm, let's say, if I got a group, and in the group I found out that the mean age of the group is 50, it should be somehow representative of the population, right? The population mean should also be somewhat 50. And if it's not, that's where the concepts of standard deviation and all these things come along. Then we'll talk about that. So when we are doing a study, we make a hypothesis, right? And the hypothesis, my hypothesis is, my question is, does smoking cause lung cancer? My null hypothesis would be smoking does not cause lung cancer, or there is no association between smoking and lung cancer. Alternative hypothesis would be there is association between smoking and lung cancer, right? So if we say if we say that our results are significant, what do we mean by that? By significant, we mean that the results I got, for example, I got results that smoking increases the odds of lung cancer. Significance over here means how whether these results are by chance or they are not by chance, they actually stand true, right? So it is basically relationship, like it tells us how the relationship between variables is caused by something other than chance alone, right? It's not just a random chance that occurred, and it wasn't just a chance that smoking caused lung cancer. It was something other than that. There was something in the smoking that caused lung cancer. This is where the concept of significance comes in. How significant is my study result? The results I'm getting from my study, how significant are they? And that's where the concept of p-value comes along. But before that, I want to talk about one other thing, is it is not necessary that if my results are statistically significant, that they are clinically significant as well. For example, my results are statistically significant that a certain medication helps decrease weight, right? And the weight it decreases it is just 1 kg in 1 year, right? Although my results might be statistically significant, but it's not generalizable, it's not working for the general population. And that's where I know that my results, although they are statistically significant, they do not hold true in the practical life, right? What would I get from using a drug for 1 year and just decreasing the weight for 1 kg? That is not clinically significant. So do you understand the difference between statistical significance and clinical significance? Statistical significance is how statistically your results of the study are significant, right? And clinical significance is whether or not your results are applicable in practical life, right? So your results could be statistically significant, but it's not necessary that they're clinically significant as well, right? Or your results might not be statistically significant, but they might be clinically significant, right? So clinical significance is basically the practical importance, right? How, is the change the drug is bringing, is it, is it something significant in the general population or no? Does the variable, the independent variable, how much is it affected by the dependent variable, right? So the dependent is weight and the independent is the drug, right? So does the independent variable, the drug, does it have a noticeable or a big effect on weight, or does it not? That would be the clinical significance of your study. I hope you got what I want to say by how clinical significance and statistical significance are different. This is very important. So whenever you hear the word significant, you always ask yourself the question, are we talking about clinical significance or statistical significance, right? So, for example, if I say that smoking increases the odds of lung cancer by 5 times, but the p value is greater than 0.05, my results are not statistically significant, but clinically they are. I will tell people that you shouldn't smoke because it does increase this risk of lung cancer by 5 times, right? Over here I would just give a very small explanation of what p value is. So p value is, whenever we do a test, we have some when the study, the authors or whoever is conducting the study, they put some level of, how much of an error are we accepting in our study. For example, let's say if I say that smoking increases the odds of lung cancer, my hypothesis was, my question was, is there any relationship between smoking and lung cancer? My null hypothesis is there isn't any. Alternative hypothesis says that there is a relationship. And then what I want to do is, if p value is a reference for comparison, I'm coming to that. So what I want to do is, let's say if someone tells me that, all right, smoking does increase the risk of lung cancer, odds of lung cancer, what I'll think about it right now is, nothing could be absolute. There can be a lot of other things that might be causing the lung cancer. And over here what I would do is, in how many cases, in how much of an error am I ready to accept in my study, right? For example, if I say that there is an association between smoking and lung cancer, what I want to do right now is I have to decide that in how many cases, you know, and what is the probability that the results I'm seeing are by chance alone, right? By chance alone. If they are by chance alone, that's an error, right? That's an error, because what I want to do is I want to look at the association between smoking and lung cancer, not just because of any other reason. So my results could be because of other reasons, because I can't say anything for sure that yes, because like I said, they might be living in an area where there is an increased risk because of the air quality, or because of some other things that are doing, right? Or genetics are playing a role, or gender is playing a role, right? So I can't be sure about it. So in how many cases am I ready to accept that error? I'm trying to explain it in very simple words, not scientific words. So scientific explanations you can always read in the books, but the simple explanation would be, for example, I say in 5% of the cases, I'm ready to accept that, all right, out of 100% probability, 5% I won't, I'm willing to accept the error. But 95% of the times, my result should be correct. There actually should be a link between smoking and lung cancer, right? This is the normal thresholds that we usually keep in statistics and studies. So it's usually 5%. Just remember this value, 5%. This is the significance level that you have set for your study now, and this is the alpha. This is the alpha of your study. We'll come to what alpha is, but you have to remember that the alpha value for our study is a 0.05 or a 5%. This is the significance level for your study. Now, what we do is, as an author, I've decided that I'm accepting that the probability that the event is happening, the lung cancer is happening, it is by chance alone and not because of smoking. And how many of the times, the probability, it's 5%, right? Which is actually 5 by 100, which is 0.05. So 5%, I'm willing to accept that. 95% of the time, the probability that lung cancer is happening, it should be because of smoking. It shouldn't be by chance alone, right? So my alpha, the significance level, write it with yourself, significance level, alpha value, this is 0.05 for my study, 5%. Now what I would do is, I will take people who are smokers versus people who are non-smokers, and then I'll conduct the study, and then I'll calculate the I'll deal with inferential statistics, take out some results. And now when I'm doing some tests, some statistical tests, for example, a t-test, for example, ANOVA, and all the tests that we do in statistics, we'll talk about them as well in our future sessions. So they give us a p-value. Then they give us a p-value, probability, that how much of it is by chance alone from my study. The probability, let's say my study took out the results that smoking increases the odds of lung cancer by 5 times, 5 times. And the p-value that came from the statistical test, you don't have to understand how the p-value comes from the test, because that's for the softwares to do. But the concept is, the test gives you, let's say the test gave you a p-value of 0.04, 4%. Let's say the test gave you a p-value of 4%. What it means is, the probability that the results are by chance alone in my study, in my sample, are 4%, right? So what had I put, how much of an error was I willing to accept initially? Can someone put in the chat box how much of what was my significance level, how much was I accepting? Anyone? Yeah, 5%. So I was willing to accept a 5% of error. What is my study showing? What is my study showing? My study shows that the p-value is 4%, which means that the probability that smoking has caused lung cancer, it could be by chance, it's not because of smoking, it is 4%. Are my results statistically significant now, or are they not? Yes, yes, because my p-value, the error I was willing to accept was 5%. My error in my study is 4%, which means that now I'm accepting my result. My results are statistically significant. Write it with yourself, imprint it in your mind. P-value has to be lower than alpha value, which is the significance level that you have set beforehand. P-value must be lower than the alpha value, for your results to be statistically significant. That's that's the bottom line of it. Another thing, let's say I did my study shows a p-value of 0.09. Are my results statistically significant or are they not? Yeah, but yeah, they are not statistically significant because the alpha error, the alpha significance level, alpha level, which we usually set and which we actually have set for our study, is when you're using the softwares in the future for meta-analysis and all these studies, that you'll see this in the software that it has a 95% confidence level, right? Also, let me put one other interesting thing. If you're putting an alpha level of 0.05, the significance level 0.05, your confidence interval, your confidence level is 100 minus 5%, which is 95%, which means that in 95% of the cases your results are not by chance alone. In 5% I'm accepting that, but 95% that they shouldn't be by chance alone. So let's say my p-value at the end came along to be 0.09. My results are not statistically significant, but my study says that smoking increases the odds of lung cancer by 5 times. My question from you guys is, although my results are statistically non-significant, is my are my results clinically significant or not? Yeah, yeah, yeah. Yani alpha level is the opposite of confidence level. A very good question. My answer to this would be confidence level is equal to 1 minus alpha. Confidence level is equal to 1 minus alpha. So if you're my question is, let's say I'm doing a study. Before that, I put my significance level as 0.10, which is 10%. What is my confidence level now? Yeah, yeah. My confidence level is, someone says 0.09. No, it would be 0.90, 0.90, which is 90%, right? So my confidence level is 90% now, which means that in 90% of the cases, my results are not by chance alone, while in 10% of the cases, my results could be by chance alone. Now, if I'm doing my study and I'm getting a p-value at the end, what should my p level be in order for my results to be statistically significant? Yeah, less than 10%. Yeah. So a p-value of 0.09 is statistically significant now. Why? Because my significance level was 10%, right? So anything lesser than a 10% wouldn't be that. A lesser than 10% would be statistically significant. If you have understood this one concept from this session, you have gotten the core of it. And you'll see this in almost every research paper. P-value was this, p-value was this, p-value was this. Now, when you look at a p-value, you must understand whether the results are statistically significant or not, right? So let's move. Let's move. I'll take one. Let's take a 2-minute break and then we can continue. Thank you. I'm glad that you understood. If you have any questions, put it and we'll continue after 2 minutes. All right, a quick summary. Everybody's asking. So, a quick summary is whenever you're starting your study, you think about, let's say you are doing a study, and I ask you a question, what your study is about. Your question is, does smoking cause lung cancer? Your null hypothesis is smoking does not cause lung cancer. Your alternative hypothesis, smoking does cause, or there is an association between lung cancer, right? Now, I would tell you that there are a lot of things that can cause lung cancer. Your answer would be yes, but what I'm looking at in my research is smoking. My next question is, in how many of the cases, how much of an error do you want to allow in your study? What should be the probability, the probability of lung cancer occurring by chance alone? How much of a probability are you going to accept? Your answer would be, all right, 5% of the 5% probability. In 95% confidence, I have confidence 95% that it is because of smoking. 5%, yes, I am willing to accept. This is 0.05 has become your significance level, which is the alpha value. Now you took groups, you did your study, you got the odds ratio, and for that odds ratio was 5, which actually meant that smoking increased the odds of lung cancer by 5. We'll talk about what odds ratio, risk ratio is in the future sessions. For now, just think about the chances. For example, 5 times. Now you conducted the test by the statistical, the tools, the softwares, and they gave you a p value of 0.04, which is lesser than the error. P value over here means that my study says that in 96% it is because of smoking. 4% there is a probability. The probability of lung cancer occurring by chance alone is 4%. I was willing to accept a 5% chance probability. My results say 4%, which is statistically significant. Confidence level is 1 minus alpha. So if your alpha is, let's say you were accepting 5% error, your confidence level is, significance level is 5. Confidence level is 100 minus 5, which is 95%. The probability of smoking causes a lung cancer is 95%. Simple words, right? So in 95%, if you take the study again, you do the same study again, in 95% of the cases your results will hold true. Your results will hold true. 5% of the cases they might be wrong. Is it simple enough for you to understand now? What is the difference between p value and alpha? The exact same difference. Alpha is what you said before you conduct a study. P value is what your statistical softwares give you after you conduct your study, and the results you get out of that. The p value, the software gives it to you based on the inferential statistics, right? The odds ratio and all that, and all the parameters. That's for the tools to do it. Our understanding should be p value we get after we have the result, after I have done everything. I've done my study, taken samples, analyzed it, collected data in my data set, variables which we talked about in the start of the session, and my descriptive statistics, inferential statistics. I got an odds ratio, and then for the odds ratio, for every inferential statistic, the tool also gives us a p value, right? So p value, both of them, alpha p, both of them are the probability of events occurring by chance alone, by random chance, not because of smoking, not because of the variable we are testing, right? So they're different in a sense. Meaning is almost same, but different in studies. Alpha, which you set, p value, which you get after you're done with the study. Is it clear enough now? Is it important in other research cases, in stat clinical cases? What exactly do you mean? I'm sorry, I didn't get your question. But of course it's important that every study has a p-value, right? Cross sectional, you get, randomized trial, meta-analysis, everything. It will give you, if you're, doing some test, it will give you a p-value, right? So we are moving to statistical distributions. Statistical distributions is, for example, uh, I'll come back to descriptive statistics. Descriptive statistics actually, the characteristics of the population, the sample population that I'm taking, and what do I use to describe them. That would be measures of central tendency, which is mean, median, and mode. Measures of central tendency, measures of dispersion, right, as the standard deviation, and then normal distribution, right, and skewed distribution. So like I said, descriptive statistics do not make, doesn't give you the results, inferences. Whatever I'm dealing with inside the sample population, this is the descriptive statistic. If I go beyond that, to the, beyond the sample population to the general population, I make some inferences. That's the inferential statistics. So statistical distributions, remember, it deals with descriptive statistics. Why? Because if I'm taking measures of central tendency, remember that measures of central tendency are the the mean, the median, and the mode. Why is it important? It's important because whenever you are doing a study, there should be, the data set that I took, the age, the weight, the, all the variables that I took in my study, the smoking, whatever. There should be, what is a one number summary of that. What is a one number sum? Nobody will ask you what is the age of every single individual. What they'll ask you is, what was the mean age of the population that you took? What was the mean age? What was the median of that? What was the mode of that? So for measures of central tendency, they're important because they give us a one number summary of the whole data set. So mean is mean is average of, all the numbers for a specific descriptive statistic. For example, let's take age. So mean would be the average, and simple formula, I hope, everybody must know that. Just add in all of them and divide it by the total number. For example, you have three people and they have age 2, 4, and 6. 2 plus 4 plus 6, divide by 3, the results that you get, that is the mean age. It is represented by x with a small, dash above it. You can check it. It's very simple. uh, there is a problem with mean. The problem with mean is that when some outlier comes in, it affects the mean a lot. For example, I had three people, age 2, 4, and 6. It's 12, divided by 3, 4. Let's say another person came whose age is 100. Now it's 2 plus 4 plus 6, 12, plus 100, 112, divided by 4. It's something around, I guess, 28 or something, somewhere above 25, right? So 20, whatever. So what the results would be, my mean changed from 4 to above 20s. It's not giving me a one number representation of my study now, of my data set now. So what I'll do is, I'll take the median of that. And median is not affected by outliers. What is an outlier? Outlier is something which is, a value which is very different from my other, from the, from the description of the, let's say if it's age, so 2, 4, 6, and then 100 comes in. That's very different. Or let's say someone is smoking 1, 2, 3 cigarettes and someone is smoking 100 cigarettes. That's very different then, right? So outlier is some, which measure of central tendency is most affected by an outlier. That's mean. Median is, let's say, you, for a median, we arrange the data set into ascending or descending order. which would be, let's say, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the middle one out of them, that's the median. That's the median. So, or let's say 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and the middle one of them. If there is no middle one of them, let's say 5 plus 6, what you'll do is you'll add both of them and you'll divide them by 2, right? So 5.5, whatever. If it's even number, that's a problem. You just take the middle two numbers, but it must be arranged in ascending or descending order, right? And then you divide it by 2 for a median. So my question is, would it be affected by an outlier? Let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and another one comes along, it's 100. Will the median be affected drastically? Not at all, right? So mean would be affected, and the median would be almost the same, right? What about the mode? Mode is a, for a certain variable, the value that's the most repeated. For example, two people have age 2, two people have age 3, five people have age 10, four people have age 6. So the 5 people have age 10, that would be your mode, right? And now I also ask a question: is mode affected by outliers or is it not? Yeah, no, no, yeah, amazing, yes, wonderful. Why? Because, for example, 2 2, and then two people have age 5, three people have age 10, and someone comes whose age is 100. We don't care because still the mode remains the same. People who the value that's the most repeating is the same. So the good thing about mode is it is not affected by outlier. Median, it is not affected by outlier. But there is another thing about that. Some populations can have two modes. What would be an example? Example would be two people have age 2, three people have age 3, five people have age 5, and also five people have age 10, right? And three people have age 50, whatever. So five people have age 10, five people have age 5. How many modes do we have? Our mode is 5, our mode is 10 now. So for this study, in this data set, we have two modes. We will call it a bimodal data set, right? If we have three modes, we'll call it a trimodal data set. The thing I want to highlight is that you might have data sets where every value of a variable could be different. For example, someone has age 2, someone has age 5, someone has age 10, someone has age whatever. It's like you have a lot of modes. Now my question is, for this data set, can you give a one number summary to to me for this data set by giving me the mode of that? Can you give me a one number summary of that? If I ask you what's the mode, and you'll be like, one person has age 1, one person has age 2, one has 3, one has 4. There are 100 modes. What do I do now? Can you give me a one number summary for that? It won't be a representative of the whole data set. So my question now is, which measure of central tendency is the best to use out of these three? Yes, someone says mean, someone says median. Median, probably median. Mhm. Which number would still stand true even if we get some outliers? I don't care. Outliers are coming. I don't care. I can still give you a one number summary with the same Mean or the same median? Yep. So when you're reading studies now, just go to the internet, just read a few studies. I'm sure most of the times you will be able to see median in there and not mean and not modes specifically. It's not absolute. There will be modes, there will be mean, but for data set, for studies which involve data sets who have unique characteristics in the variables, there would be mean in most of the cases, as opposed to there would be median in most of the cases, as opposed to mean or a mode, right? So this was measures of central tendency. I hope everybody understood it. After 2 minutes, we'll talk about measures of dispersion. I do understand it would be better to use a board, but not everybody was able to see it. Let's try. Let's try. Okay, let's try if you guys can see it. Let me get a whiteboard. Okay, can you open the whiteboard now? So one question, 10, 20, 30, 40. How do we determine the median? It's already arranged in ascending order. So what are the middle two values? It's 20 and 30. Add 20 and 30, it's 50. 50 divided by 2 is 25. 25 is your median. Yeah, thank you for everybody who answered. Can you see the board? I already shared the link above, and no, can't see. I don't know why, but okay. All right, unable to open. Let's skip and look at this now. Look at this screen. I'll try to explain from here. Can everyone see this screen? Yeah, for next session, please download the whatever app it is. Please share in the group then, and we can then talk about it. So, all right. So we talked about measures of central tendency. This is something I want to show you now. Look at this. Uh, uh, okay, it will open in new tab. So what I'm trying to do is just showing you in the same tab. I don't know what the heck happens to this, but All right. All right. So, oh my God. Yes. You guys can even open in your own. Wait. 1 second, okay? All right. Isn't it possible to take it on YouTube or some other app which is easily accessible? I don't know, but let's continue with this. Can you see the graph? I can't zoom it because it will take it to another screen. I'm sorry, I'm not a very tech pro person, but okay. So this is a normal distribution. For a normal distribution, where this is also this is the histogram. If you make a histogram, let's say age, and a lot of people have age. Let's say it starts from, let's say it's 0 and 1, 2, 3, 4, 5, whatever, 100, and 50 is in the middle. So let's say a lot of people have an age of 50. What would happen is that it will give you like a big bar over here, then smaller, 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 and smaller, smaller, smaller. If you make a curve over this data, it will give you a shape of a bell. A shape of a bell. This is also known as a bell curve, right? So what happens is, for a normal data, let's say it starts with 0 and it ends with 100. Where will the mean lie? Where will the mean lie? Where will the mean lie? Will the mean lie over here on the left, or on the right, or somewhere here at the center, right? Yes. So mean will be here, right? Mean will be here. Where will the median lie? Where will the median lie? Hmm. Yeah, median will also be over here, the 50 almost, right? Over the top, over the top. Where will the mode lie? If this is something you have to understand. Where will the mode lie? Mm-hmm. Someone says same. All right, yes. So what will happen is your mode will be over here as well. Why? Because if a lot of people have age 50, this graph will go up, 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 and to the top. If let's say 100 people have age 50, 99 people have age 49, it will be a lower graph. Then 80 people have age 30 or somewhere, it will be a lower, right? uh, Age 10, it would be very less people, so it will give you a histogram like this. So the most repeated value, if it's 50, this will go to the top, and the shape you will get out of it would be something like this, whatever is made already. So your mode, the most repeated value will be in the middle, your mean will be in the middle, and your median will be in the middle. So in a normal distribution, no, it won't be everywhere. It won't be everywhere. It would be at the top, because this bar is made by, let me show you, this thing, right? So let's say 10 people have age 5, 20 people have age whatever, and age 2 would be, let's say, 30 people. Let's say 100 people have age 4, so for 100 this would be at the top, and the graph you'll get would be something like this. So which one is the most repeated? 4 is the most repeated, because 100 people have age 4, so your mode is 4 over here, right? Am I clear enough? I'm trying to explain it in very simple terms, so I hope that's not very difficult to understand. Someone give feedback? Yes, thank you. So for a study which has for normal distribution curve, For a bell curve, your mean, median, and your mode lie at the top. Your mean, median, and mode lie on the top, right? And this is all of this is area under the curve. Area under the curve, it should be equal to 100%. It should be equal to 100%, right? One second. Let me open another screen. It will be give me a little time. I'm sharing it on. Yeah, thank you, Azaz, for yeah, for a normal Gaussian distribution, the mean is equal to the median is equal to the mode. Very important to understand. Is the screen visible? Yeah. 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 Okay. So for a normal standard distribution, the mean is equal to the mode is equal to the median, right? Now, normally, normally, what's now? I'll come to measure of dispersion. For a measure of dispersion, what we give is standard deviation. Standard deviation. This thing, right? Standard deviation. So what does it say? A statistic that measures the dispersion of a data set relative to its mean and is calculated as the square root of variance. Forget about it. Let's discuss in simple terms. What is standard deviation? Standard deviation is how spread out how spread out the data is from the mean. The data are from the mean, right? How spread out, this is the mean, this is the mean. How spread out the data. Do does everybody has a value of 0, or let's say we put 50 over here for age from 0 to 100. Does everybody has an age of 50, or no? Some people have 30, some people have 20, some people have 70 or 80. How spread out the data are from the mean, right? So normally, this is, if you consider one standard deviation, this is deviation. In simple terms, how deviated the data is from the mean, right? So let's consider this as one standard deviation towards the left, one standard deviation towards the right, two standard deviation towards the left, two standard deviations towards the right, and three towards the left, three towards the right. Remember, this is an empirical rule. Empirical rule says that 68% of the data 68% of the data are within one standard deviation of the mean. 68% of the data will lie over here, right? 95% of the data lies in between two standard deviations of the mean, right? And 99% of the data lies in between three standard deviations of the mean. For a normal distribution, 68% of the data are within one standard deviation, 95% are within two standard deviation, and 99.7%, or to be precise, or 99% of the data lies in between the three standard deviations, right? So what it means is that almost 68% of the people in the general population will have an age which is within one standard deviation of the mean. For example, the mean age is 50 and standard deviation is 10. It means 50 minus 10 is 40, 50 plus 10 is 60. It means that 68% of the people in the population will have an age which is between 40 and 60, and 95% of the people will have an age which is between 30 and 70. 50 plus 10, one standard deviation, plus 10, two standard deviations, 30 and 70. And 99% of the population will have an age between 20 and 80, right? 20 and 80, right? 50 plus 30, 50 minus 30 is, 20 plus and 80, right? This is the range. This is the range. This is the range. 20 is the lowest value and 80 is the largest value. What is range? Range is, the high highest value minus the lowest value, and the range would be 80 minus 20, which will be 60, but we'll talk about that later. For now, our discussion is about standard deviation and normal distribution. In normal distribution, 99% of the data lies between within three standard deviations of the mean, right? So let's say the size of the standard deviation is very low. For example, mean is 50 and standard deviation is 5, right? Which is 45 and then 55. Let's say standard deviation is very low. What will happen is that a lot of the data will accumulate towards the center, because a lot of people now have weight somewhere, have age somewhere over here. So what would happen to the what will happen to the bell? Would it become tall or would it become flattened? Would it become tall or would it become flattened? Tall. Tall, yes, yes. So if the standard deviation, okay, how about if the standard deviation is very large? If you, let's say, mean age is 50 and standard deviation is 20, then think about the data within 68%, the 68% data within one standard deviation, and then this two standard deviations, and then three standard deviations. Would this become taller or would it become flatter? Yeah, it will become flattened. This is a simple concept that you have to understand. So yeah, so this is for us, for a normal distribution. Now let's discuss skewed distribution. Yeah, skewed distribution is when these are the tails. This is the tail, this is the tail, this is the top, right? Let's say head, and these are the tails, for example. So if one tail is longer, in a normal distribution, if you look at this, both tails are of equal length, right? But if one tail becomes longer, one tail becomes longer, when will it become when will it become longer? It will become longer if most of the values lie towards this side. This tail will become longer, which means most of the values are now above 50, for example, above 50. So what will happen is that you'll have a lot of data points over here, and your results will become, your curve will become skewed. Curve will become skewed, and right skewed and left skewed is on the basis of the tail. Which tail is longer? If the right tail is longer, this is a right skewed. If the left tail is longer, it is a, if it is it's a left, or in other words, it's a negative skew. It's a positive skew, because most of the data is now towards the positive end. In here, most of the data is towards the negative end. So in a normal symmetrical distribution, mean is equal to the median is equal to the mode. But median, if median is here, for a positive skew, since most of the data lie here, in calculating the mean, since mean is the sum of all the values in a variable divided by total number of the values, it will be, if a lot of values lie here, your mean will shift from the middle towards the right, from the middle towards the right, towards the positive side. But mode would still be, just look at the topmost point, which means if you make a histogram, let's say this is 40, so a lot of people have age 40, and that's why your mode is here. So the top is always the mode, the top is always the mode, the top is always the mode. Mean is towards whichever the side towards the most of the values lie. Mean will be that. Just take any data, let's say make your own data, 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 5 plus 10, you know or make it about. And if you increase the data and when you actually calculate the mean, your mean will shift towards, let's say 1 plus 1 plus 1 plus 1 is 4, and then 5, 10, whatever. If you calculate the mean for a proper data, if most of the values are lower, your mean will be towards the lower side. If most of the values are higher, your mean will shift towards the higher side. Your mode will still be, the number of most repeating. And if you look at one thing, an important realization over here, you can still see median is the legend. Median is still standing somewhere in the middle. See, over here it's still somewhat, it's not changed that much, even though there are a lot of values that are lying over here now. It will get affected because there is not just one outlier. There are a lot of outliers now. There are a lot of data who has the data set has shifted towards the right, towards the positives now. It has impacted it somewhat, but it still lies somewhere in the middle. However, look at the losers, the mode and mean. They have shifted towards, to whichever way the data is carrying them. So that's why the winner becomes median always, and that's why it is often repeated. I hope we are clear to up till here. If someone has a question, you can put. We'll take a little break, 2 minutes, and then we'll continue. So I suppose there aren't a lot of questions. Positive skewed explained, so I think almost everybody explained that. Positive skewed is, in simple words, when a lot of data points for a specific variable, a descriptive statistic, for example age, for example weight, for example, let's say smoking, if it lies more towards the, let's say 5 people have age 10, and 10 people have age 50, but 80 people have age 80, 90. So your data will shift from a normal distribution towards a positive skew. Most of your data points lie towards the right now, towards the positive, and that's why your results are being skewed. That's a positive skew. Negative skew is the opposite. Significance is that, like, whenever this is important, whenever we are considering a data, how, how, if I ask you, you took a data set, you took 50 people in smokers, 50 non-smokers, and I ask you, what was the age of the people, and then you're like, okay, some people had age 5, some people had age 10, some people have had age this much. I'll ask you, can you be more, can you make it easier and just tell me a one number summary for that? You'll tell me, okay, the mean age was this, mean age was 50, mean age was something like this. But what about my, if my data is not normal distribution, what if it's not symmetrically distributed? What will you do then? What you'll do in that case is, you'll give me a median of the data, now that the median age was, let's say, 49, 45 or something. And another significance is that for a symmetrical distribution, I can easily tell that, all right, if you tell me the mean and the standard deviation, I'll tell you how many of the people will have an age which lies between these specific points. I can't be sure that, everybody has this much weight, but I'll tell you is that, all right, the mean is 50, the standard deviation is 10. What I'll tell you is, so that means that 95% or almost everybody of the population, they're aged between 30 and 70, right? I'm not thinking about 100 now. So if you tell me it's normally distributed and you just tell me about the mean and standard deviation, I can easily make inferences from that, right? I can use them then. The other topic for us is types of data, and does outlier affect the internal validity? Outlier affects the internal validity. Think about it. Think about it. Internal validity is dependent upon descriptive statistic. Descriptive statistics is the age, whatever, the gender, which we talked about, smoking. And now what you're doing is, one of the descriptive statistic, for example, smoking, 50 people, you took 50 smokers, and out of those 50, 40 are smoking 5 cigarettes a day, right? But what happened is, the rest of the 10, they're smoking 500 cigarettes a day. Outlier is something which is very different, right? So 10 people are smoking 500 cigarettes a day. What will happen to your results? What will happen to your results? Outliers have occurred. Your descriptive statistics have been disturbed now. Your internal validity is low now, right? So simply put, if you put in a lot of outliers, your internal validity is decreasing. And that's why when we collect sample, we randomize it. What do we mean by randomization? By randomization, I mean, close your eyes, take 100 people, and randomly put 50 people towards one side and 50 people towards the other side, not on the basis of, on the basis of age, not on the basis of ethnicity, not on the basis of where they're living, in a specific city. They can be living anywhere. You're taking them and you're randomly distributing them. The only thing that is making a difference as to who will go to group A and who will go to group B for our study would be what will be the only thing that will decide that these people are going to group A and the other ones are going to group B, for a study which is looking at the association of smoking and lung cancer? What would be something that would decide that, okay, yeah, exactly, smoking, the variable that you're testing, the variable on which you'll make inferences. Apart from that, I don't care if I put 50 people towards the left, 50 people towards the right, group A and group B. I'm closing my eyes. I don't care whoever goes to which group. Whoever. But let's say I'm like, okay, let's put these youngsters to group A and let's put these people towards group B. Let's put people from uh, place A or a city A to group A, and people from city B to group B. What? How about, probably probably city A has a good quality of air, and then your internal validity has decreased. Now there are differences. Now group A has all the people, group A is all the people who have, let let's say, a bad air quality. Group B has all the people who are coming from city, which has good air quality. And now group A are smokers, group B are non-smokers, and the results I'm making is that smoking is associated with lung cancer. How would you say if the good or bad air quality, the bad air quality in city A is not contributing to that? So the conclusion is, whenever you're considering your variables, your sample population, you have to take care of all the descriptive variables so that your internal validity is high, and for your results to be significant, right? And so that your results are, it will increase the internal validity, as well as if your results are significant, the inferential, it will the inferences that you're making, they'll be statistically significant, also may or may not be clinically significant as well. We'll end up with discussing the types of data. Types of data is data, like we said, it's like a set of all the variables that you're putting into your study, and this the summaries, the conclusions that you make. Data is like, it can be of two types. It could be quantitative or qualitative. Quantitative could also be called numerical. Qualitative could also be called categorical, right? A quantitative data could be discrete or continuous. Right? Discrete data is in which there are just whole numbers. For example the for example the the number of years in a med school, right? Number of years, that would be year 1, year 2, year 3, year 4, year 5. There is no year 1.5 or something like that. There's I'm a first year student, I'm a second year, I'm a third year, I'm a fourth year, I'm a final year student, right? So what will happen is, these are the discrete variables now, because the numbers are whole numbers. But if it includes fractions, if it includes decimals, what would we call it? We'll call it continuous variables. And continuous variables are, let's say age, let's say height, let's say BMI, let's say weight. It could be 1.5, it could be 2.3, it could be 5 point whatever height, it could be 6 point whatever height. So this is the quantitative data, as well as you can call it numerical. However, keep in mind the types, it could be discrete or continuous. A qualitative data, as well as, which is also known as categorical, it could be either nominal or ordinal. Nominal is when there is no logical order to the data. When there is no logical order, like for example, gender, it could be male, it could be female. For example, religion, it could be Islam, it could be Christianity, it could be uh, whatever religion. So it's not like there is an order to it. There is no logical order to it. For example, blood types of people, it could be type A blood, type B, type AB, type O positive, O negative, A negative, A positive. It's like there is no specific order to it. Right? But for ordinal data, there is a logical order. For example for example the severity of pain from 1 to 10, it would be, like, let's say if I want to make it categorical, I'll make it 1 to 3 would be, let's say the least pain. And let's say make it lower degree. And from 4 to 6, let's make it middle degree. And from 7 to 10, let's make it a higher degree pain. So we have three categories now, based on a logical order, from 1 to 3, from 4 to 6, and from 7 to 10, right? My question is, uh, can you calculate the mean for an ordinal data? Qualitative data, two types: nominal, no order; ordinal which has a logical order? Can you calculate the mean for an ordinal data? All right. So the answer is, interestingly, no. Why? For a mean to calculate, for a mean to calculate, there must be quantitatively same difference between the categories of the variables that you're making. Let me repeat. For for you to be able to calculate the mean for a variable, the quantitative difference between the different categories should be quantitatively same. For example, 1 to 3, right? That's the lower degree. For the middle degree, it's there are four, like 4, 5, 6, and for the higher degree it's 7, 8, 9, 10. There are four now. So is the quantitative difference between lower degree and middle degree pain the same as the quantitative difference between middle degree and higher degree pain? Is it same quantitatively? No, no. Let's say for age, for age, for example, 1, 2, 3, 4, 5 years, 6 years, 7 years, and up to 100. Can you calculate the mean for age in this case? Age being a quantitative data set, data variable. You can calculate, yes, because the quantitative difference between 1 and 2 is the same as the quantitative difference between 2 and 3 and 3 and 4 and so forth. but but for an ordinal data, let's, for example, degree of pain that I gave, the quantitative difference is not same in between the different categories of the variable. For example, if I ask you depression, for example, depression, and categories are lower degree, middle degree, and higher or severe depression. And in I make a scale. For example, I make a scale. I ask you certain questions. This is research relevant, so please focus and understand this. If, let's say, you're doing a study on, let's say it's about depression or anxiety or something, and you're making categories now. You made a questionnaire, and now you're asking people about about their daily life, their working hours. Do they have thoughts like they're useless, and do they have thoughts like of suicidal thoughts? And on the basis of that, you're like you're giving them score, for example. And the scores are, let's say your categories are, if someone scores 3 out of 10, I'm putting them in lower degree depression. 5 out of 10, 6 out of 10 would be middle, and 10 out of 10, 9 out of 10 will be severe depression. Now, is the quantitative difference between a lower degree of depression and middle degree of depression the same as middle degree or higher degree? No, because you can't quantify that. And that's why we cannot calculate the mean for an ordinal variable, right? So yeah. Another question I want to ask is, can you calculate the median for an ordinal variable? What is a median? What is a median? What is a median? Median is the middle variable. The middle variable, right? The middle variable. And median is relevant to order. You have to arrange them in ascending or descending order. So let's arrange it. Lesser degree, middle degree, higher degree, it's order. That's why we are calling it ordinal variable of quantitative data set. If they are in order, can you calculate the median? Yes, we can, because the middle one out of them is the median. Simple. And can you calculate the mode? Yes, by all means, yes. For example, out of 50 people, 25 people had middle level of depression, 10 people had a lower degree of depression, 10 people had higher degree of depression, or 15, whatever, and 25 have middle degree. What is the mode now? The mode is middle degree of depression, right? So you can calculate the median, you can calculate the mode for median, again the winner, median again the winner. Mean you cannot calculate for an ordinal data, which even though it has an order. But interesting thing is, ordinal variable of the quantity of the qualitative data type has the, the significance is that you can calculate the mean with the median, and you can actually put like this is the median for this data. So there are a lot of other things to discuss, but I think it won't do justice to the to the timing now. I'm opening the setting where you can open your mic, and if someone has a question you can ask. We'll we'll have a 5 minutes question answer session, and then we'll end the session depending on if you have questions. Anybody? Last things I said. So what did I say? What I said was that there are types of data. There are two types of data mainly: quantitative or qualitative. Quantitative can be discrete or continuous. Qualitative can be nominal or ordinal. Nominal where there is no specific order. Ordinal where there is a specific order. For example, degree of depression, degree of pain. For example, the severity of kidney disease, where there are five stages: stage 1, stage 2, stage 3, stage 4, stage 5. There is a specific order. If the GFR decreases from this level, we call it stage 1. If it's this, we call it stage 2, stage 3, and increasing level of severity, this is an ordinal variable. I also mentioned that for quantitative, yes, it's quite obvious that you can calculate the mean, median, and mode. However, for a qualitative data, you cannot calculate it the mean, because the quantitative difference between the different categories of a categorical or qualitative variable is not the same, right? But you can still calculate the median and the mode for one type of qualitative data, which is the ordinal type, because it has gotten a specific order, right? Is that clear now? Which is more common, quantitative or qualitative? I can't be sure I can answer that, but like whenever we are conducting a study, it has all kinds of variables. It has all kinds of. If you are conducting a meta-analysis in the future, like if it's a drug which is affecting the heart, but it also has some other outcomes. Let's say my study is the efficacy and safety of a specific beta blocker in heart failure. Now, this beta blocker can affect the ejection fraction of the heart. It can affect the septal diameter of the heart, the interventricular wall, the thickness of it. But it can also affect, let's say, one of my outcome can be mortality. How many of people in the group to whom I gave the beta blocker versus to the other group to whom I gave a placebo, no drug? How many of people died in this group? How many of people died in the other group? So for this, my question from you guys is, what kind of a variable is this in types of data set? Which type is this? Mortality? Is it categorical? Is it numerical? Yes, categorical, because someone died, someone didn't die. Yes, no, yes, no. So can you give the mean for this? Can you give the mean for this? No, you cannot give. So you have to give the total number of events in the treatment group versus the total number of events in the control group, right? So this will come along very handy when we are doing systematic review and meta-analysis, which would be the end goal for all these discussions. But these foundations are very important to clarify. A lot of people struggle with understanding the basics of this. So if you understand it well, you'll find it very easy to at least understand when you're reading those studies. Can be the quantitative order same in ordinal? I'm sorry, I didn't get your question. What exactly do you mean? If you want to go for research, which one will be easier for us, quantitative or qualitative? Again, are you thinking about a cross-sectional study that you usually do in university? If yes, I'll say both of them are equally, you can do both of them. But my personal preference is shift more towards review studies. Try to understand how to do meta-analysis, systematic review, narrative review. We'll talk about that in our future sessions. That's for future sessions. But do understand these basics. And for a cross section study, you'll have to collect data and do all that stuff. For review study, you don't really have to do that. But we will talk about case reports and other stuff which you can easily write. So any other question? No questions are in categorical research. I am not sure what do you mean by categorical research. I was thinking about that. What are the faults of yeah, there is no fault of a cross-sectional study. Every study, like I said in the previous session, every study is a good study. Every publication is a good publication. The downside is for a cross-sectional study, if you're doing a very a really good study in which you're going to the hospital, you're doing you're looking at some intervention that's happening, you do a retrospective or prospective cohort, or a case control study. Cross section is just a snapshot in time. You look at the prevalence of something, and in a population, let's say, um, for example, the awareness about something, or the prevalence of a specific disease, which as well is a really good thing. But like I said, it falls in the lower portion of the hierarchy of evidence. Look at the last lecture and you'll understand what I mean by this. So is it possible for ordinal data to have some quantitative difference? Yes, ordinal data does have some quantitative difference. For example, lower degree, middle degree, higher degree. But the problem with it is that it's not a well defined equal quantitative difference between the different categories, right? If the difference is not equal, you cannot give the mean out of that, right? But it has its own significance. A qualitative data has its own significance, quantitative has its own significance. But the quantitative difference between the different categories, it's not the same. You cannot say that severe depression, and if it's kidney disease, stage 1 and stage 2 has a difference of some degree of GFR. Stage 4 and 5 has a major difference, stage 5 being a stage of kidney disease in which the kidney isn't even working at all. So how can you compare the difference between stage 1 and stage 2 to the difference between stage 4 and stage 5? We can't approach to clinical study or cases in first 2 years, so we can carry with cross-sectional study. No, you definitely can. Why can't you do a review study? You don't have to do any clinical work in order for you to be able to write a systematic review or a meta-analysis or a narrative review, right? You don't have to go anywhere. You just have to sit, you have to search the literature, find some gap, and you write which is the which is at the top of the hierarchy: meta-analysis, systematic review. So why wouldn't you start with doing something which you can do just by understanding how to do it and finding the relevant literature and starting to write on that? Even for a case report, we wrote some cases in which we had people who weren't actually who didn't actually had the clinical exposure. But you just have to, if I tell you it's a case on aplastic anemia, and you sit there and you search the literature and write the introduction, do you think you need the clinical exposure for that? I don't think so. You just have to understand how to do it, and then you can carry it along from there. We do have a session on literature review and manuscript writing in the future. Close ending questions are part of categorical data. Close ending questions. I don't really get your question. If you can please explain it. Read by AOs. I have a question. If we conduct meta-analysis, do we have to go through all the studies on PubMed regarding the specific topic we are considering? If you have watched the previous session, I'm sure you'll understand. You'll get the answer to this. But it's not, you don't have to, you have to search you have to put in the keywords, the search terms, and the results that you get. You extract that, you screen the studies, and then you include those studies. It is a whole long procedure. And the next question is, will we have a session on meta-analysis? Yes. Yes, basically, this session is a session on meta-analysis. If you understand the difference between different types of data, variables, if you understand the significance of p-value, alpha, if you understand the difference between, symmetrical distribution, and the all the things we discussed today, you are going to see the same things in while you're doing a meta-analysis. You will have to divide the outcomes on the basis of whether they are descriptive or whether they are quantitative, right? And then when you're extracting the data, you have to understand what kind of a variable it is, and then you'll be able to do that. But for that, you have to stick along and take all the lessons. And what we are doing is we are discussing the basic biostatistics in the first few sessions, maybe for a week or 10 days or 2 weeks, whatever. And after that, we'll discuss case report, systematic review, narrative review. And then the last sessions would be on meta-analysis, in which we'll actually discuss how to conduct a meta-analysis. And uh, all the things that we are discussing now, they'll come in handy over there, right? We'll be able to, yeah, after attending session. Close ending means yes no questions. So a yes no question, yes no question would usually be categorical, right? Categorical, like for example, um, did people die? Yes. Did they not die? Yes, no, whatever. So if it's a yes no answer, that would be a categorical. But if it's like a continuous, it's age, it's something like ejection fraction, it's 10%, 11%, 15%, that would be quantitative data. Yeah. No, like, do you have to go through PubMed, Google Scholar, and a whole lot of databases to consider? Yep. For a meta-analysis, systematic review, the general guidelines by the Cochrane Library. You can just search Cochrane, Cochrane. That's they've given the standard guidelines on how to conduct a systematic review. And on that, they have, I think, I'm not exactly sure, but I think they've written that you conduct search of at least 2 to 3 databases, let's say PubMed, Google Scholar, and you can add in Scopus or some other database. So just one database, it wouldn't be considered that strong and credible, because you can miss out the studies which are included in the other database. So I think that's about it. If someone has a question, you can put it here, or we will end the session in a minute. Also, I might be sharing a feedback form, which you should please consider uh, filling then, so I'm able to understand how easy it is for you to understand the topics and what exactly should we focus on. So you're very welcome, and we'll communicate in the group. Thank you so much, and goodbye. Have a great night.